Good morning, everyone. We are from Group 3, and today we will be presenting our practical exercise 2 project under the subject Enterprise Network. Our presentation will walk you through the objectives, network setup, discovery, troubleshooting steps, and the documentation we prepared as part of this exercise. Before we begin, let us introduce ourselves. I am Sriram, and with me are my teammates Sivabalan and Andakumaran. So on this slide, we focus on discovering all devices connected to our network. So first, we use discovery tools such as the show CDP neighbors command or perform manual tracing to identify every device in the network. This allows us to map out how devices are interconnected. Next, for each device, we record important details including the IP address, MAC address, device name, model, and operating system. This ensures we have a complete inventory of the network. It's important to note that some logical interfaces like sub-interfaces or SPIs may not appear in the discovery results, so we need to account for them separately. Finally, we highlight any missing or outdated information in our records so we can plan for updates of other investigation. Here we demonstrate how to discover all devices connected in our network using Cisco Discovery Protocol or CDP. First, on each router, we enter global configuration mode with quantity and enable CDP using the CDP run command. This allows the router to share and receive device information with its neighbors. Next, we use the show CDP neighbors command. This lists all directly connected devices, including their device IDs, local and remote interfaces, platform type, and capabilities. For example, from our router 1, we can see neighbors R2 and R4 with their respective interface connections. We repeat this process on each router R2, R3, and R4 to build a complete map of the network topology. This output helps us identify the device's names, connections, ports, and capabilities. However, it's important to note that logical interfaces such as sub interfaces or SPIs may not appear here, so we need to document those separately. By recording this information, we can maintain an accurate inventory of our network and quickly spot any missing or outdated device information. For this part, we focused on discovering all the switches connected in the network using the show CDP neighbors command. On switch 1, S1, we found a direct connection to router R1 through the gigabit 0/1 interface. Switch S2 also detected its neighboring devices successfully. For switch S3, the result showed multiple connections to a router R2, including several sub interfaces, which indicate VLAN configurations. Switch S4 initially had CDP disabled, but after enabling it with CDP run, it displayed its connected neighbors. Finally, the multi-layer switch SWMLS showed links to router R4 with several sub-interfaces representing different VLANs. Overall, these results help confirm all switch to router connections and give us a clear map of the network topology. In this step, we use the show CDP neighbors detail command to collect more specific information about each connected device. From router 1 R1, we can see detailed data for R2, R3, and R4, including the IP addresses, platforms, software versions, and interfaces. For example, R1 is connected to R3 via gigabit 0/0/1 and to R2 and R4 through serial interfaces. On router R2, the details confirm its connection back to R1 using serial 0/1/0. For router 3, R3, the output shows its connection to R1 at IP 192.168.2.1 through the gigabit interface. Finally, router R4 shows a direct serial connection with R1 at IP 10.20.20.1. Overall, this command provides deeper insights into each device version, interface, and platform, which is very useful for documentation and troubleshooting. Next, we use the show CDP neighbor detail command on switch 1 S1 to gather more in-depth information about connected devices. The output shows that S1 is connected to router R1 through several interfaces, gigabit 0/0/0, as well as sub interfaces 0/0/0.10 and 0/0/0.20. These represent different VLAN connections configured between the switch and router. Each entry also provides useful details like the router's IP address, platform model, Cisco ISR 4300, and software version. This detailed view helps verify not just the physical connection but also the logical VLAN setup and the device's operating systems. Next, we view the detailed CDP results for switch S3 and switch S4. On switch S3, the show CDP neighbors detail comment shows multiple links to router R2 using interfaces such as gigabit 0/0/1, 0/0/1.50, and 0/0/1.60. This indicates that the switch is connected to different VLANs on router R2. For switch S4, the details show connections to router R3 again took several sub-interfaces like 0/0.70 and 0/0.80 representing separate VLAN connections. This detailed output confirms the switch to router connectivity along with each router's IP platform and specification, version, helping us verify the network structure accurately. Finally, we check the CDP details for the multi-layer switch SWMS MLS using the show CDP neighbors detail command. The output shows multiple connections to router 4, including several sub-interfaces such as gigabit 0/0/0, 0/0/0.90, 0/0/0.100, and 0/0/0.110. Each sub-interface represents different VLANs configured between the switch and the router. The command also provides router's IP addresses, platform type, and software version, confirming that all interfaces are active and communicating properly. This completes the device discovery process, giving a full overview of every connected router and switch in the network. So in this step, we use the command show IP interface brief to list all active interfaces and verify their IP addresses and status. From the output, we can see that each router R1, R2, R3, and R4 has multiple sub-interfaces configured such as 192.168.10.1, 192.168.30.1, and so on, which represent different VLANs or networks. We also confirm that most interfaces are up and operational while some are administratively down, meaning they are manually disabled. This helps us ensure all network connections are properly configured before continuing to the next troubleshooting or verification steps.
Good morning, everyone, and sir. My name is Natkumaran. So here we can see the S3 show IP interface brief. So this is the fast Ethernet and LAN one connectivity. So this one is uh, switch, and this one switch 4. For test 2 is we have to test the connectivity among devices, test communication using ping or trace route between all devices. Second, identify devices that cannot communicate properly. Third, record connectivity results and highlight any failed links. Our first test from PC1 to R1 was successful. This confirmed that some parts of the network were configured correctly and functioning as expected. However, when we tested LP2 to R2, the connection failed. These results show that there might be a misconfiguration or interface issue that require further investigation. The next test is PC4 to R1 and R3 also failed. This indicate a possible gateway or routing problem affecting multiple parts. Finally, the test from LP2 to R1 and R4 failed as well. These repeated failures confirm that we had several configuration or connection error to resolve. For the question 4, we have to analyze the default gateway configuration. First, access router or switches and review gateway interface configurations. Secondly, we have to check IP address, LAN or sub interface setup and port status. Lastly, highlight any missing or incorrect configuration. Troubleshoot phase introduction. Based on our test results, we began a structured troubleshooting process. Our goal was to restore communication between all devices and ensure complete network connectivity. Step 1, enable CDP. The first correction was to enable CDP on routers R1, R3, and R4. Once enabled, we could detect neighboring devices properly, which made identifying link problems much easier.
Good morning, everyone. My name is Siva. Today, I'd like to explain some of the troubleshoots over here. Okay, the second one is we found that PC1's default gateway is incorrect. So we changed it to the correct subnet gateway, allowing the PC to communicate beyond its local network. So as you can see, okay, now it can be pinged by all the IP addresses. The third problem is that we discover that an interface on switch 2 was administratively down. So after issuing the no shutdown command, the interface came back up, restoring communication for connected device. As you can see, we can ping from laptop 3 to the switch to the router 2 through the switch 2. So this is the proof that the interface turned up. We can see here the red color turn into a green color. The fourth problem is to change the IP address on R3. We noticed that the IP address on interface G0/0.80 in router 3 was configured incorrectly. So after assigning the correct IP address, R3 successfully joined the OSPF network and routing stabilized. Okay, the fifth problem is to change the OSPF on R2. R2 had missing OSPF configurations, so we correct the process ID and ensure all the interfaces were properly advertised in OSPF, enabling the dynamic routing between all routers. Okay, the last one is to change some of the cables in this topology. So we made some following corrections from starting from laptop 1 until PC5. After making these changes, all devices were physically aligned with their logical design. So this photo shows the proof that we changed the some of the cables in this topology. Now we are at task 5 is to create device documentation table. After reconfiguration, we repeat our ping test. This time, all devices successfully communicate with each other, confirming that the network was now stable and correctly configured. Okay, the final step is to create the device documentation table. So the table lists every device's name, role, IP address, MAC address, VLAN or interface model, and configuration summary. It serves as an official record for network maintenance and troubleshooting. So, in a conclusion, this project enhanced our practical networking skills and teamwork abilities. We would like to thank our lecturer, Inchi Sharul Nazmi bin Ismail, for his support and guidance. That concludes our presentation. Thank you for listening.